Welcome Regents students. The topic of today's video is the Bohr model. But before I go into the Bohr model, I just want to review what we learned so far in this modern physics topic. The first day, what we learned is that waves, electromagnetic waves, can actually act like particles on a submicroscopic level. Just want to remind you that electromagnetic waves are anything from this spectrum. AM, TV, radio waves, microwaves, visible light, ultraviolet, X-ray, all of these on a submicroscopic level act like little bullets, which we call photons. And they crash into things like electrons, and they produce these effects, so therefore they have momentum and energy given by these two expressions. So waves are particles on a small level. Then we learned in the second video that particles behave like waves, or are waves, on a submicroscopic level. So we're talking about electrons, protons, and neutrons. They are not solid things flying through space and crashing into things. They are waves with crests and troughs, and they can do all kinds of things that waves can do. Pass through things, pass through each other, interfere with each other, be in multiple places at one time. And I mentioned that the behavior, if you really had the time to look at all the fascinating phenomenon that occur because of this, basically it's like, almost like, as I said, like magic, okay? And these waves, we can calculate the wavelength using the de Broglie expression, or if you have advanced mathematical ability, maybe you're a physics student in college, you can use the Schrodinger equation, not just to calculate the wavelength, but also the amplitude, wavelength, and frequency, how these things vary in time. So the question is this really true, this remarkable stuff that makes up matter, all protons, neutrons, electrons? Turns out that in physics and science, the way we answer such a question is obviously through experimentation. And that's what brings us to today's topic, because the success, probably the greatest success of this quantum theory was to explain the atomic spectrum. Basically, if you take glass tubes and you fill them with gases, here, these glass tubes, if we're in class, I would show you them, but now I have to just resort to showing them on the from an internet picture. But these glass tubes would be about this long, okay? And they'd be shaped this way, filled with, say, hydrogen gas or nitrogen, oxygen. You could fill these tubes with any kind of element from the periodic table that can be in a gaseous form. You pass electricity through it with a high voltage. So electricity or energy is passing through this gas. And you would see in class, I would show you different samples, and you would notice with your eyes alone that different tubes of different elements created a different sort of glow. You could see that here. And then if you got even more precise through experimentation, and you had a setup like this is a schematic. You took that glass tube and you passed the light that came from it through a prism. What you would find is that a particular glass tube would create a series of colors. Now this is just showing a full rainbow right here, this top box. But what would come out of the gas that's excited by electricity is just certain lines of colors, okay? Or if you wanted to, you could pass white light into that gas and you would see white light's a full rainbow. And instead of the gas creating these colors, it would subtract them from the white light, pull them out, in other words. And this might be like hydrogen, but you would find, if you studied all the elements, that each element had its own sort of signature of colors that it created, like almost like a fingerprint. So you could take an unknown sample of gas and light it up with pass electricity through it, and you could then look at its spectrum and look at tables and determine what element you're dealing with. It's a way to identify each element. So in other words, each element releases certain exact colors. And that was known before quantum physics, okay? But the problem was no one could explain why that happened. Then comes quantum physics, this unusual, bizarre theory about the nature of atoms, that they're waves, that the things that make up atoms, electron, proton, neutrons, are actually waves. And this then is able to finally explain away this mystery. It was a tremendous achievement for the theory. And so that's what we're going to be learning about today, that sort of success. So this is just a diagram of what the pictures on the internet showed. So we have an emission spectrum. We excite, this is called an emission spectrum. We excite a gas with electricity or some other way, and then it releases light, and we pass it through a spectrometer. I split the word up, but it's spectrometer. And then that splits the light up or spreads it out, and we see that certain colors are emitted for a particular element. So this says specific colors or frequencies, like a fingerprint for each atom, for each element on the periodic table. Or you could do an absorption spectrum. You pass white light through a non-excited gas and pass that light that comes out through a spectrometer, and it's the full rainbow minus these colors. So I didn't draw it because then I didn't have a way to color it nicely and subtract out those colors. But full rainbow minus the same colors, color lines above. So the question is, how did quantum physics answer or explain this away? So that brings us to the Bohr model. Okay. Okay, so remember, the electron is actually a wave. It's not a particle, not a solid little sphere. It's a wave, so when it orbits in a hydrogen atom, which has just one proton in the middle, then we've got a wave wrapping around the atom. And what this diagram shows is that when the atom is in the non-excited state, the smallest possible orbit you can have is for one wave to fit in a circumference. Waves have crests and troughs. So let's suppose there's a crest here. 180 degrees later, there's a trough. When the wave comes around again, we have a crest meeting this crest. And so we have a crest and a crest meeting. What follows crest is a trough. So you see, as this goes around, crest always meets crest, and trough always meets trough. We call that constructive interference from the wave unit. Whenever a crest and a crest meet, they add to make a bigger crest. And as we saw in the video yesterday about waves, particle waves, then when the amplitude grows, that increases the probability of finding some particle in that particular vicinity. So when you have constructive interference, the wave is reinforcing itself, that orbit is allowed for the electron in the hydrogen atom. The lowest one, where one wavelength fits into one circumference, we label that n equals 1, and we call it the ground state, the bottom possible orbit. If you add energy and you try and boost this up, so if you add it, you're like lifting it to a higher orbit. Okay, let's suppose I give it a little burst of energy. So now notice this orbit's bigger than this one. And now what could happen is, instead of the trough, after following the crest here, because the orbit's larger, the trough is here. So crest, trough, what follows crest, trough is a crest. What follows crest is a trough. So the next time around, the wave is a trough right there. And then the trough is followed by a crest. And you see that crests and troughs are always meeting. So when you have two waves and a crest meets a trough, we call that destructive interference. The amplitude adds to 0. Maybe we have, in terms of a rope wave, positive 1 meter and negative 1 meter adding to 0. So that means if the wave function has 0 amplitude, that means the electron can never be in that orbit. So I cannot add energy to get to here. So let's suppose instead of giving this much energy, I give even more energy. So I get to even a high, I try and put the electron into an even higher orbit. What might happen in this case is a crest, followed by trough, followed by crest, followed by trough. As that wave wraps around, the next time around, what we have is after a trough, we've got a crest. After a crest, we have a trough. Notice we have, again, constructive interference. That means the wave is allowed to be there because the amplitude grows. Constructive interference, that's what we label as the second orbit, the n equals 2 orbit. So let's suppose I try and give even more energy to an even higher orbit. What might happen then is I would have a crest here, a trough here, a crest, trough, crest, and then look what happens the next time around. After this crest, we've got a trough. After the trough, we've got a crest. So that wave, that electron wave, will cancel itself out if it tries to go into this orbit. Destructive interference. That means it's not allowed to go there. Because whenever the amplitude is 0, the probability of finding the electron there is 0. So it can never go here. So instead of adding enough energy to go here, let's add even more energy. What can happen in this case? Crest, trough, crest, trough, followed by a crest, followed by a trough. Once again, we get constructive interference. So we have 3 wavelengths in the circumference. We call that the n equals 3 orbit. And then we can go into 4 wavelengths, 5 wavelengths. I don't need to draw those. You get the idea that it's whenever an exact number of wavelengths fit in an orbit, the electron is allowed. This finally explained why these elements had these atomic spectrums. They could only, the atoms could only jump to different orbits, and that corresponds to different kinds of energies. Tremendous success of quantum physics was explaining that away. Now, how do you figure out what these energies are? So basically you could do computer modeling. Bohr had his own calculation. That's what we're going to move on to next, what we call energy level diagrams. So in your reference table, you'll find some energy level diagrams right here on page 3. I drew hydrogens here, not quite to scale, otherwise these energies here would be crunched up more. Just so we could talk about the concepts of how these orbits change. So, notice I've got my n equals 1 here, my n equals 2 there, n equals 3 here, 4, 5, 6, this is infinity. Infinity means that the electron is completely out of the atom. So basically the way physicists decided to label these energies is to consider when the electron is outside of the atom, free, as energy equal to 0. What that does is it switches our thinking around a bit, because then what's happening is the electron, instead of climbing from out of the ground state, we think of it as falling from outside the atom inward. So when you fall into the atom starting at 0 energy, how do you fall or decrease energy from 0? You have to have negative energies. So these energies, the energy levels of all atoms are negative because they fall from being free into the atom. Okay? Keep in mind that that kind of switches the thinking around on you. You may think of this to here as a decrease in energy, because if you ignore the minus sign, it looks like 13.6 is bigger than 30.4, so we're losing energy. That is actually incorrect, because think of this. What's more, being in debt $13.60 or being in debt only $3.40? This would be like increasing your wealth. So these are increases in energies. Even though the numbers look like they're getting smaller, the energy is actually increasing. So let's suppose we've got our electron in the ground state. And let's suppose, hypothetically, we try and give it energy. How do we give it energy? Well, we could pass electricity through it, like we did with those tubes I showed you. or you could shoot it with photons. And so let's suppose you bombard it with a photon that has 10.19 EVs. So that's what I show right here, 10.19 EVs. If you subtracted these two energies, you would find that the difference from here to here is 10.2. So 10.19 is just shy of getting to this energy, the n equals 2 level. 10.19 EV is not enough energy, so the atom absorbs no energy. That 10.19 EVs passes right through the gas sample and no atom will take it. And every single atom that it passes, the electron stays in the ground state, if they're all in the ground state. That makes sense, and it's understandable. Like if you had $10.19 and the movie ticket cost $10.20, you wouldn't be able to get in. So that makes sense. If you get a burst of energy exactly 10.2 EVs, the electron will rise to the n equal 2 state because it has enough to get to that step. Okay? So the atom absorbs the energy and the electron rises from the n equals 1 to the n equals 2 level. Okay? But here's something that's unique and a little counterintuitive. Let's suppose we now have the electron in the ground state and we give it or try to give the electron 10.21 EVs. It only takes 10.2 to get to the n equals 2. So we're giving it a little bit extra. Now in the case of money and purchases, like if you went to a movie and it was a movie ticket was $10.20 and you had $10.21 in your pocket, obviously the movie person would let you in. Not so with these electrons. In the case of having just a little bit more than the energy required, the atom will not absorb it. It'd be like the person at the movie theater in the booth saying, sorry, you can't go to the $10.20 movie because you have $10.21 in your pocket. Sorry, go home. Right? So a little unusual. The atom will not absorb. It needs exactly the amount to get in to the next state. No more or no less. And the electron stays in the n equals 1. It does not go there. Let's suppose you give the electron 12.09 EVs. If you subtracted these numbers, you would find that that's 12.09, the difference between this number and that number. In other words, that's just the right amount of energy to go into the n equals 3. So that is allowed. The electron goes from state 1 directly to orbit state 3. So it would go like this and jump right to here, bypassing that orbit. Okay, straight from 1 to 3. What about if you had two photons? The first one gives the electron a burst of 10.2, and then the second one gives an additional 1.89. That is also allowed. The difference is now instead of the electron jumping straight up in one shot to 3, it would first go with 10.2 EVs into the n equals 2, and then with another 1.89, it would go the rest of the way to the n equals 3. So it would go one at a time up through those states. But if you had two photons, one was 12.0 and one was 0.09. In other words, first photon takes you here, and maybe the rest one would take you the rest of the way, giving us a complete 12.09, as in here. Nothing happens. Even though these two photons add up to the amount of energy necessary to get to here, the atom stays in its original state. So the energy must be given in one burst with one photon to get to the next level. You could go one burst up multiple levels, but you need an exact amount to always land on a certain energy level. That's why we call the fancy word for that is the energy of an atom is quantized. It comes in fixed amounts, or it's released in fixed amounts. Never, it's like a staircase. You can walk to step 2, step on to the third step, fourth step, or you could take a giant step and go from the first step to the fourth step if you've got long enough legs, but you could never step to the 2.9 step. It doesn't make sense. You always have to land on an exact step with energy. And one final point, if you get energy, any energy greater than 13.6, it's allowed. The energy is not quantized anymore, because once you get enough energy to go completely out of the atom, the electron is free, and the energy is no longer quantized or bound by fixed steps. So we'll look at an example of getting more than 13.6 to escape the atom in the third example problem that I'm going to do. All right, so a lot of concepts there. Make sure you understand all the possibilities of how the electron can jump from different orbits, okay? And how it has to, the particulars of the ways it has to absorb the energy to land on exact orbits. Let's move to our first example. Okay. So, an electron begins in n initial 5 and n final 2. First question, is the photon released or is it absorbed? Then, determine the energy of that photon in joules, and then determine the frequency, and then determine the photon type. The first thing, the electron is released. That's my answer. How did I know that? First of all, the energy level diagram that you copied on the previous page, you're obviously not going to use that to solve problems. You're always just going to go into the reference table. Okay, so here we are. What we do is we see that when we go from n equals 5 down to n equals 2, we're going down in energy. Yes, negative 0.54 to negative 3.4 is a decrease. You're becoming more negative. And if the atom's losing energy, it has to be releasing it. So that means the photon is released. The second part, well, how do we calculate the energy in joules? First thing we got to do is find the energy in electron volts. So what we do is we get the two energies off the reference table. The n equals 5 is right here, a little hard to see because they're kind of scrunched up. You come over here and you see that it's negative 0.54 is the initial energy. And the final for n equals to negative 3.4. So the way you can figure out the change in energy is by just subtracting final minus initial. I always put absolute values because in the end, we just want the energy of the photon. So it doesn't make sense for it to have negative energy. It's either absorbed or released, and the quantity is the absolute value of the subtraction of the two. So I have negative 3.4 minus a negative 0.54, which really makes plus. And that comes out to negative 2.86. But again, I take the absolute value, and the energy of that photon released coming out of the atom is 2.86 electron volts. Okay, so the next thing, they asked for the energy in joules, not electron volts. So remember, this I talked about in the first video, how to make the conversion. You take the electron volts and you multiply by a fraction. We're going to want to put the electron volts in the bottom of that fraction and joules in the top, so that the electron volts will cancel away, leaving us with just the joules. Now, where did I get this 1.6 10 minus 19th? Front cover of the reference table. This is where you get all the numbers. So we need to find the conversion between electron volts and joules. So in this first table, we go down here, we see 1 for electron volts and 1.6 10 minus 19th for joules. So we put the 1 for electron volts and then this number for the joules. So what we're doing is multiplying this and then dividing by 1, giving us the energy. There it is, the energy in joules of that photon. The next thing, well, what's the frequency? Well, remember, there's expressions for the energy that you don't have to remember. The energy of a photon. We go to our modern physics section. We see that if we want the frequency, we use this expression, hf. If we want the wavelength, we use hc over lambda. So obviously we're using E equals hf, and that's where I begin. So I put my energy in. This, by the way, always has to be in joules. You can never plug in the EV value. If you plug in the EV value, you're going to get the wrong answer here. So always make a conversion into joules. All right, so what is H? Again, front cover of the reference table. So we go down here, we look for Planck's constant H right here, 6.63 10 to the minus 34. Don't forget the units of joule seconds. So there it is. Solve for F 6.9 times 10 to the 14th hertz. And then the last part, determine the photon type. So what we do is we go into the electromagnetic spectrum and we look for, first of all, 10 to the 14th hertz. That's between here and here somewhere. We see that it falls into the visible light spectrum because we're at 6.9. We're between 7.69 and 6.59. That is violet light. So that's where I got that answer. I look up on the this could have come out to like 10 to the 15th, then it would be ultraviolet light, right? So it could vary. It could be any one of these in the reference table when you're identifying it, but that's how you identify. Next example. An electron in the mercury atom is in the C state. It absorbs a photon of this given wavelength. Determine the energy E E of the photon in electron volts, and then the final state. So, back to our reference table, the energy level diagrams. Hydrogen here, mercury here. The hydrogen ones, as you've seen already, the energy levels are labeled with numbers. In the reference table, they give you one other element, mercury. Of course, we would, in general, we would need one of these for all the elements of the periodic table, but Regents confines to just analyzing these two atoms. The mercury levels are not numbered, they are lettered. Okay, so we're saying we start in the C level and we absorb energy, so we're going to go up to a higher level. What level do we get to? Well, this is how we figure that out. So, first thing, the energy in electron volts, first we got to get the energy in joules. So we go back to the modern physics section and we look for our formula. Here it is, E equals HF. No, we don't have the frequency, so we don't use that one. We use HC over lambda. Okay, so E equals HC over lambda. H we get, again, from the front cover as we did before, right here, 6.63 10 to the minus 34 joule seconds. Then C is the speed of light, okay, which is actually the speed of all electromagnetic radiation. We look for C right here. Oh, I passed it right here. Speed of light in a vacuum, 3 times 10 to the 8 meters second. So that goes in for C, and then the lambda was given. Plug that on the calculator, and I get my answer, 2.9 times 10 to the minus 19 joules. But they asked for the energy in electron volts, so once again we've got to do conversion. This time, instead of electron volts in the bottom to cancel the electron volts as we did over here, leaving us joules, we want to put the joule in the bottom so that the joules cancel, leaving us the electron volts in the top. All right, well, that's where the units go. What numbers do we go? What number goes with electron volts? What number goes with joules? Again, front cover of the reference table, 1 electron volt. So 1 goes with electron volt, and this goes with the joules, the 1.6 times 10 to the minus 19th. So that goes with the joules. This goes with the electron volt. So what we're doing is we're taking this number, multiplying by 1, and then dividing by that number gives us 1.81 electron volts. Now the question is, what energy do we end at? Well, this is the energy we started. Since we're absorbing a photon, we're going to go up to a higher energy. We're going to go up this many EVs. So we start here and we go up 1.81. And so the final energy is negative 3.71 EVs. Well, that's the energy, but we want the state. So we go to our reference table and we look up what state is negative 3.71. We find negative 3.71 right here. So we went from here to there, okay? What's the letter of that? Oops, why did I write C? The letter of that is 3.71 is actually letter E, okay? Well, easy to fix. There we go, okay. Final state is E. We went up from here to there, which is state E, from C to E, okay? All right, one more example, but this one's this little short one, so, okay. All right, an electron is in the C state again. It absorbs a photon with 7.23 electron volts, and it's asking us to determine the kinetic energy of the liberated electron. So as before, we can find the final energy by taking the initial. Since we're absorbing the energy, we're going to add that. If we were losing energy, we would subtract, right? Because you would go, if you lose energy, you go down to a lower level. So you would subtract this. But since we're absorbing energy, boom, we're going to a higher level. That's why we have the plus. We're adding that. And we get to positive 1.71. Now, as I said, all the energy levels, whether it's hydrogen, mercury, oxygen, all the energy levels are always negative. You're falling into the atom. It's like a hole when you get stuck in the atom. So if we have positive, we're inside no atom. Okay? The electron is broken free. The fancy word in chemistry when you break an electron free of the atom is you ionize the atom. Right? That's why this says ionization at the top. Okay? And that extra energy is now kinetic energy. It flies out of the atom with kinetic energy. Now, you cannot plug that into 1/2 mv squared because the energy in kinetic energy 1/2 mv squared has to be in joules. So if you wanted the speed, which I don't do because I think this video is long enough, but if you wanted to calculate the speed, you could. First, you would have to calculate the joules of this. That would be like the calculation we did back here, right here, converting to joules. So first you would do this conversion with this energy, and you get the joule value of this kinetic energy. Plug that in for Ke, the mass of the electron, 9.1 10 to the minus 31, front cover of the reference table, and you could solve for V. So that is it. Okay, the Bohr model of the atom. Okay, stunning proof of explaining away these atomic spectrum. Why does an atom, every atom, give off different colors that are unique to it, that basically ID the atom, okay, or absorb the same energies? It's because a little particle isn't orbiting around like the Earth going around the sun, okay? It's not like that in the atom. It's a wave going around, not a solid particle electron. So only certain possible orbits are possible because we need an exact number of wavelengths to fit, electron wavelengths to fit in the orbit. That's the concept, the why. And then you need to be proficient in this. Actually, probably not much on the Regents about it. Okay, I'm just explaining it why because it's fascinating. But this, understanding all the concepts of how the transitions, which ones are possible, which one are not, you need to know that, okay? That we need to land exactly, more or less, not going to happen, okay? So that concept, and then we did some calculations, how to figure out the energies and frequencies and so on and so forth, okay? The last thing I want to mention is that explained the spectrums, okay, this stuff. But even more remarkable was this. If you take a computer and you load this into all the various atoms of the periodic table, the conditions of the electrons orbiting, you put in the voltages, and you let the computer generate the wave functions. What happens is it generates certain shapes. Let's see, yeah, that looks like I could see it on the screen. Okay, These are the orbitals in chemistry, the s,p,d orbitals. Remember the octet rule. All of chemistry is explained by this remarkable theory. Why the octet rule? Why do electrons like to be in eights around an atom? Schrodinger's equation. So this is the heart, the orbitals, of why we have CO2, why we have H2O, why do we have DNA molecules. It's explained by the orbitals in all the rules of chemistry. And then why are those rules correct? Because of Schrodinger's wave equation. So that was what was so remarkable to those physicists. Remember those quotes I showed you about how profoundly disturbed they were by all the things that were happening in the way that atoms behaved or particles behaved. And they were forced to accept it because this basically explains away everything. Okay? It is so powerful. It's so universal. It explains chemistry, physics, and then all these bizarre behaviors then are proven by all the chemistry that we already know. Okay, so that's basically the remarkable story, or a little piece of the remarkable story of quantum physics. Okay, the Bohr model was a tremendous success for the theory and all that followed from it.